Hello. Uh, in this video, I'm going to be going over the notes on energy. I wanted to start with a quick little overview of what you did in the previous assignment with this energy skate park simulation. So if you remember, you watched first this woman skating back and forth in a perfectly frictionless world. She would keep going back and forth forever. And I just want you, hopefully you noticed that when she's at the top, she has lots and lots of potential energy, but no kinetic energy. And at the bottom, or as close as I could, she's basically all kinetic energy with almost no potential. And the total energy is staying constant the whole time. When we introduce friction into the equation, hopefully you noticed that she's still at the top, has the most potential energy, and at the bottom has the most kinetic energy. But over time, you have this thermal energy slowly increasing. And as the thermal energy increases, she's going slower and slower and less high. And that's because of friction. You can feel this energy. If you take your hands and you do this, you create friction and you can feel the thermal energy that friction is generating. Okay, so those are the key points from that simulation. So now the notes. So the definition of energy in physics is an object's ability to do work. And we'll have a little lesson on work probably next week. But the basic idea is work is just a force acting over a distance. So the more force needed, the more distance, the more work. So this weightlifter, we can increase the work he's doing either by increasing the amount of mass, meaning the amount of, which would increase the amount of force he needs to lift it. You would also have to do more work if he had to lift it a further distance. Lifting it only a little bit is less work than lifting it a lot. So energy, an object's ability to do work. So there's three main kinds of energy we look at in physics. Well, there's multiple kinds, but broadly, potential energy is stored energy, energy that's not in use, but it's available to be used later. By the way, all of you that have taken chemistry, this is kind of review, like it's review, but we're approaching it from a bit of a different angle, but it's the same idea. So different kinds of potential energy. There's chemical energy that's stored in food or batteries. This is, in chemistry we learned, this is energy that's actually stored in the bonds between the atoms. If you remember me injuring myself with the rubber band bonds, good times. There's also electrical potential, which is also in batteries and generators. We're going to focus a lot on gravitational potential energy. This is potential energy you get from lifting an object above the ground. And later we'll also look at spring or elastic potential energy. This is from compressing or stretching and holding. So that rubber band had elastic potential energy. So gravitational potential energy is what we're going to focus on right now. This is energy that is stored due to an object's height above a surface. Think about it as their potential to do work. Like in simple words, what is the potential an object has to like do damage when it falls? So if you think about like, you know, a big rock, how can it do the most damage when it falls? You want to lift it to the highest height. Like the higher the height, the more damage it can do because it can accelerate more and create more force. And the other thing you can change is the mass. The bigger the object, the more energy it has. So, like on this roller coaster, it has the most gravitational potential energy when it's at the highest point possible. So the formula for that is on your reference tables as the change in potential energy is equal to the mass of the object times acceleration due to gravity times the height, or the change in the height. So if you got rid of the change, it would just be potential energy is mass times gravity times height. And then if it changes, you can figure out how much it changes. So that explains why in our simulation, it had the most potential up at the top here, because it had the most height. No matter, so depending on where they are on this hill, the height can change. What doesn't change is the mass of the person and the acceleration due to gravity pulling them down. So the only thing that really changes as they move is the height. So that changes their gravitational potential energy. The other kind of energy is kinetic energy, which is energy of motion. In chemistry, temperature is a measure of the average kinetic energy of the particles. How fast are they moving? Kinetic energy in physics is just energy being used by an object in motion. The formula, it's 1/2 times the mass times the velocity squared. So the faster an object's going, the more kinetic energy it has. Also, the more mass, the more kinetic energy it has. So yeah, anytime an object's in motion, has kinetic energy. If it ever stops moving, then it has no kinetic energy because the velocity would be 0. The last kind of energy that you saw in the simulation is thermal energy, also known as internal energy. This generally refers to energy that is converted to heat due to friction. And so in the real world, there's no such thing as a perpetual motion machine, like that skateboarder that just goes back and forth forever. In the real world, that wouldn't happen because the potential energy doesn't get perfectly converted. We have some energy being converted to heat because of friction. So there's different examples here. When a meteor burns up in the atmosphere, its kinetic energy is getting converted into thermal from all the friction with the gas in the atmosphere. You got a burnout, you got someone starting a fire, and this is actually how we light matches. The energy from friction, from the sliding, helps give it the activation energy needed to get the reaction started. So the total energy of a system, though, remains the same. So we talked about in chemistry the law of conservation of mass. The full law is the law of conservation of mass, energy, and charge. Just like mass, energy is neither created nor destroyed. It's just changed from one form to another. So an object that's at the top of a track, like a roller coaster at the top of a track, has lots and lots of potential energy, but no kinetic. And as it goes down the track, all that potential gets converted into kinetic. In a perfect world, ignoring friction. In the real world with friction, that energy slowly gets converted into heat, thermal energy, which gets kind of lost to the air and distributed to the particles of the air. So eventually all that energy that the object has gets transferred to the surfaces it's interacting with and the air, which is why you can't have a perpetual motion machine. By the way, that's an interesting rabbit hole to fall down if you want to Google perpetual motion machines and the quest for them and how theoretically they're impossible. It's kind of cool. I hope these notes were useful. There's a few questions at the end to answer. Tomorrow, you'll do some math with it. I hope everyone's okay, and take care.